Friss transmission equation. Now this horn is radiating maybe max in this direction and this horn is receiving in this direction. So they are looking at two different directions, right? If I transmit a certain power PT, I want to know how much is the power that I can receive PR. At the end of the day, that's what I want to know. From a system designer perspective, I tell you that, hey, if this guy transmits 1 kilowatt, I should be able to receive at least, let's say, 1 milliwatt. Only then my sensitivity is there. I can establish a communication link. So I will just put a requirement like that. Then it becomes the antenna engineer's job or the base station radio network planners engineer's job to determine what should be the transmit power of this, how should it be oriented, what is the maximum range you can have, so on and so forth. To do that, this equation called as the Friss transmission equation, Friss, Friss is the name of the guy who discovered it, becomes useful. What it essentially tells you that is, when I have an isotropic radiator that radiates equally in all directions, and if I transmit a power PT, at a certain distance r away, if I'm at a certain distance r away, then the power density that I see, power density, which is this many watts if I transmit at this location r, if I were to see how much is the power per unit area that I get, that's going to be that many watts per meter square. That's the power density. But if I were to, that's the power density that you would have if you were to use an isotropic radiator that radiates equally in all directions. But if you were to use a non-isotropic, that means you are additionally having a gain of G, then your power density is going to be this term multiplied by a factor of G. That's the gain you have in that particular direction. So that's true for a non-isotropic radiator, which is mostly the same, mostly the case for a communication link. For example, in a wireless base station, then the base station is going to be directional. It's going to have a gain in a particular direction. So this becomes the transmitter's power density, which is watts per meter square. Notice that it's 1 over r square. Yeah, there's a 1 over r square dependence. And G being the gain in that particular direction that the antenna is looking. Gain is in the particular direction that the antenna is looking. So now, if this is the power that is received, this is the power density that the receiver sees. If I place a receiver in this direction, let's say I put a receiver here, the RX is placed at this point, then the terminal power at the receiver that I would be able to receive is going to be the power density that it sees times the area, the effective area that we just saw. So this is going to be in watts per meter square, and this is going to be in meter square. So totally, I would get the power received in watts. And remember, AE is lambda square G over 4 pi. So if we go ahead and substitute that, we can go ahead and say that A, what is the received power for a given transmitted power? That turns out to be this equation here, which gives you, depending on the wavelength, depending on the distance between the transmitter and receiver, depending on the efficiency of the transmitter and receiver, and depending on the directivity. So this directivity is linear, not in dB. You have to know when to use dB and when to use linear. Yeah. Now this term, right, this lambda square over 4 pi r, right, there's nothing you can do about it. Meaning, if you want to have some power transmitted, but you want to be able to receive something, you can go ahead and change your gain because that's under your control. You can go ahead and change the receiver gain because that's under your control. But you need that range R that is not under your control. And you need a certain frequency of operation, and that is not under your control. So this entire term is the physics that brings it into the equation. And this is not under your control, whereas this and this are under your control. So if this value is high, then you can have these two as a low value. But if this value is low in the first place, then you have to have these two as very high. So this particular term, the lambda square over 4 pi r square, is called as the free space loss factor. And since loss is the negative of gain, you can define the loss in dB as negative 10 log 10 of lambda over 4 pi r square. So that's the free space loss in dB.